Well, first of all, thank you for giving me this opportunity. I don't belong to your community, as you probably understand. I belong to a nearby community. I'm a seismologist, more specifically a seismotectonicist, and I'll show you why. This is my title. My co-authors are mostly from OGS, except for Stefano Parolai, who's now with the University of Trieste. So it's clear that earthquakes are a crucial issue, both for storing CH4 and for CCS. The nightmare of people designing a storage site is that there is a fault beneath the reservoir that generates a large earthquake. And this was pretty much not considered until a few years ago. In 2012, you may remember, we had two large earthquakes, semi-large earthquakes in the Pole Plain on 20 and 29 May, magnitude 6.0 about, causing victims and causing a lot of damage. The second event, the 29 May, was generated by a fault which had been known for many years from seismic data, which was chosen for developing a geologic gas storage facility. Of course, after the earthquake, this plan was abandoned. After these earthquakes, people started wondering whether there was an anthropogenic origin to these events, or if there was another reason why they occurred. Now, we all started to work on this theme following an intuition by Marco Mucciarelli. Marco Mucciarelli is a colleague of ours. He was a director at OGS until he died, unfortunately, in 2016. What he said, what he noticed was that above the surface projection of the seismogenic fault responsible for the second event, the 29 May, all the wells, all the drilling that was done was turned out to be sterile, totally sterile, whereas there were productive fields in the neighboring regions. And he thought that maybe the reason for this lack of gas in the region was due exactly to the fact that there was a seismogenic fault there. The Italian government put together an international commission called the CASE. You may remember this case. This commission decided that perhaps they came up with a slightly ambiguous conclusion that human activity may have triggered the earthquakes, or maybe they didn't. Anyway, we decided to explore these relationships between large earthquakes and faults. Large, by large I mean something of magnitude 5.5 and above, and in particular to explore the relationship between productive or sterile deposits versus earthquake. We wrote two papers, one in 1215 with 400 wells, a larger paper 2 years ago with almost 600 wells, and over a much larger region of the Po Plain. The context, the Italian context, is rather simple in this case. We have the Apennines running from the Po Plain to Sicily, which are today an extensional province, and we have compression to the northeast, east, and to the south of the region undergoing extensional faulting. So compression concentrate in these areas, and these areas are the same areas where there's been hydrocarbon development since the 1950s. A typical anticline of the Po Plain is shown here. This is in fact the anticline that gave rise to the 29 May earthquake. This is a schematic view where you see the fault down below at a depth of 3 to 6 kilometers, maybe a little more. And on top of the fault, you see exodus faulting, which is a common occurrence in anticlines of this type. The seismological context shows that seismicity concentrates along the axis of the Apennines. They are mostly extensional earthquakes, as I said. There is some deformation, compressional earthquakes also in the Po Plain and in the Adriatic. This situation, this difference between the Apennines and the Apennines to the east is shown by the seismic hazard map of Italy that shows the highest hazard along the Apennines and moderate hazard in this region and to the south. Now, there are a few facts and hypotheses I would like to put forward. The preservation of any type of gas accumulation, CH4, CO2, hydrogen, requires that the caprock is intact, not broken by fractures and faults. We've talked about this a lot today. Basic principle of search mechanics dictate that a method of this size from 5.5 on may rupture through a significant thickness of the crust. For instance, the 7 kilometers that we're seeing is a typical depth which may be ruptured by an earthquake of this size. And an earthquake of this size may generate or reactivate fractures, may cause slip on the secondary faults. For instance, the extrados faulting I was showing may break, essentially breach the caprock and cause gas to escape. We've been speaking about leaks a lot today in previous presentations. And the question is whether this is the mechanism that applies to our regional investigation. The basic data we use are seismogenic sources up here. This, incidentally, this is the core of my activity for the past 25 years. Historical seismic earthquake data down below, and the Videqui database, which is an Italian glory, I could say, is a unique database storing lots and lots of information, precious information that we used extensively. We also considered this 18 seismogenic sources, which gave rise to 16 historical earthquakes. For two sources, we don't have historical earthquake. Probably it was too early to be recorded, but we're positive that all these seismogenic sources may generate earthquakes of the size we are talking about. So this is the exercise we played, calculating 3D distances between all the 1561 wells and the 18 seismogenic sources that I just showed you. And this is shown in this map here over a region which includes part of the Po Plain, part of the Adriatic, and so on. We used the weight of evidence method, which is a method that evaluates the likelihood of a certain hypothesis, calculates a weight of calculates a positive and a negative weight of evidence and the contrast C, which is the parameter that's then used in the interpretation. Positive C is a good correlation, means that the hypothesis we are making is reliable. Near zero, there is an insignificant correlation, and if C is negative, there is no correlation at all. The hypothesis we are making is just not confirmed. And these are the results. If we start from to the left, we see the productive gas fields, which tend to be to fall in the classes 20 to 30 or 30 to 40 kilometers. So that means that productive fields tend to concentrate away from the seismogenic faults. If we look at unproductive gas fields, we see the opposite. We see that they tend to concentrate near the seismogenic faults. Now, this is the result that comes from statistics. Let's look into one of these particular cases. Medolla is a locality of the Emilia Plain where there are gas seeps that are called terre calde. This existed since the 1800s. The yellow box in the middle is again the projection onto the surface of the 29 May earthquake. And we know that these terre calde are essentially gas seeps that leak continuously. Been doing this for centuries probably and do it today. Now, if you look at this evidence, Chav and others were measuring the contents and the concentration and contents of these gas seeps. Have been doing this for several years, starting in 2008. And they showed that when the earthquake occurred, there was a sudden increase both in the quantity of emitted gases and also in the concentration. There was more methane coming out than the other gases. And this has been lasting for a few years before subsiding. Now, if you look at the right, we see that the anticline is clear in the topography and that the gas seeps locate exactly on top of the anticline, exactly where we expect extra-dust faulting to occur. So the bottom line is that probably uh, this gas seeps go on every day for life, and they are rejuvenated when there is an earthquake, which means that for a few years there is an increased flow, which then comes back to normal. But evidently, the leak is continuous. The implications essentially are that the presence of reductive wells may help identifying areas where the fault down below is essentially creeping, not producing earthquakes. Whereas the absence, the absence of productive wells indicates that probably the fault below is seismogenic, so is a place to be away from. And the second main conclusion is that depleted reservoirs guarantee the safety of a prospective storage sequestration site, in my view. Also, the pre-exploitation history of that reservoir guarantees that it may sustain the pressure of an intact gas field. This is a sort of explanation, theoretical basis for this process. What's interesting is that the Italian industry probably didn't know why, but they've been carefully avoiding the most seismic portions of the region I've been working on, which is here. There are seismic faults, there are historical earthquakes, and there is no gas production from this district. And all the other operations have been located in different areas. So they don't know why they did it. And I guess this is the end. Thank you.